There we go. All right, so today, final thing on rough paths was going to be, I want to talk about the sewing lemma. Okay. All right. So let me remind you of a couple of things that we have done so far. First of all, remember in the rough path and a rough path lift, it is a non-unique, right? But we are able to sort of tell, what rough paths, or what the different rough paths look like as an increment of a function, right? So recall that, we have this Chen's relation. Which says that x2 st minus x2 su minus x2 ut is equal to x1 su times x1 ut, right? So we have this kind of triple difference on the left-hand side is equal to that over there. So let's say you have one path, x1, and you have a rough path above it. So this is a, rough path 1. And then you also have a second rough path above it, x tilde, which is the same underlying path, but a second order process is different, right? And what you can do is if you take the difference between x and x tilde, you look at x minus x tilde, say at st. Okay. Then we have that this is just subtracting the two Chen's relations, SU to SU minus XUT, UT tilde is equal to 0, right? If you just subtract the Chen's relation for both of these. Now you can show that if you define A of ST to be XST minus X tilde ST, this difference. Okay, then what does this say? This says that AST minus ASU minus AUT is equal to 0. And then one other thing you can note in this particular case is that A of S comma 0 is minus A of 0 comma S. You can just check that from Chen's relation as well. You kind of have this. In general, you're not going to have that. In general, you're going to have to add on some products of the increments of the original function.
There could be a two in the definition.
Yeah, sorry. Yep, that's right. So you can check that A satisfies this property. And then if you just let U equals 0 here, then you get A of ST is equal to A of 0T minus A of 0S. Okay. Absolutely. So it's exactly that. And then this, I'm going to define this delta operator, which is exactly as you say. So the point is, if this delta, the delta operator I'm going to define as this triple difference is equal to 0, then A is going to be the increment of a function, right? You're able to split A into A of T minus A of S, right? You're able to do the splitting. All right. So, and conversely, you can always take, and you can just verify that if you take the increment of a function and then apply this kind of triple difference, that you're always going to get 0, right? Yeah, exactly. Yep, that's right. So, let me just define a operator. So given a function A, given A from the 2 simplex to say RB, something like that, we can be RD, you know, R B by D, no, whatever, just, you know, have some codomain. Then we can take, then we can define the triple difference, delta A S U T as A S T minus A S U minus A U T. Right. So what we've shown is, at least if we have this kind of a symmetry in A, that delta A equals 0 if and only if A is the increment of a function, right? So we can also define, if we have of other functions, say I, just on the of one parameter to say our D by D, blah, 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 right? Then we can define its single, you know, delta operator as delta I of ST is I of T minus I of S. And what we've shown here is that, you know, delta I is always identically 0. Before, right? And then also we can have kind of the inverse, as long as we assume that that one condition over there about A of S comma 0 being minus A of 0 comma S, that if the delta operator on a function of 2 variables is 0, then it's the increment of a 1 variable function, right? So the Sewing lemma is interested in an approximate version of this, right? So if delta of A is approximately 0, is delta of A approximately an increment function? Let me give a hint of why we would care about this, and it comes back down to another proof or another example that we had talked about. So the other example we had talked about, or computation, was, remember, if F was in C1, X was in C alpha, say alpha between 1/3 and 1/2, right? We were able to do this. So we wanted to define what this was, right? In order to do that, we Taylor expanded F and got F of S plus F prime of S, S to T, X of R minus X of S, dx of S, plus something that was little o of T minus S, right? So if we Taylor expand it, and then the hope was sorry, we had that, and then there should be a X here. Sorry, should be. Yeah, so we Taylor expanded this. And then, yeah, give me 1 second. It should be, yeah, we should expect it to be f of s, x of, oh, sorry, that should be an r, right? On the left, yeah, it's confusing. That should be an r, right? Was that?
Both counters will just do that. Same thing on the limits. They're just that's another S.
Yes.
It's a different S.
Yeah, so you're able to, kind of do this expansion, right? And you have this little o of t minus s here, we hope, right? So x of s. Sorry about that. X of s here. Yep. Sorry about the confusion. So you have f of x of s, x of t minus x of s plus f prime of x of s times this iterated integral, right? Plus something that is little o of t minus s, right? So if we call all of that, so the whole idea or the whole hope of rough paths theory was if we're able to define this, and we have these guys, which we already know, then we're able to define this guy. That's the whole hope, was if we were able to define, this thing here, which I'm going to call a of s comma t, right? Then we can find a integral over here. So the hope is define a of s comma t, which is equal to star. Okay, which we've been able to do. So we have the Lyons-Victor extension theorem and some other things. So we're able to define this a of st. Now we just need to check that our hope was right, that we're able to define this left-hand side, right? So this is good. Next, want to define, the integral from s to t, f of x of r, dx of r. And if you notice, this is actually the increment of a function, right? It's the increment of the integral from 0 to t minus the integral from 0 to s, right? So the problem we're interested in is given a function a of st, so problem, given a of st, which is called a germ, can we find continuous linear I, so that I of t minus I of s is equal to a of s comma t plus little o of t minus s. So the point is, before we had that this triple difference operator was 0 in a lot of cases, if and only if you're the increment of a function, right? But what if we're not interested in it being exactly 0, we're just interested in it being approximately an increment of a function with a little o of t minus s here, right? And then if we're able to define this, then we can define, this integral as whatever this guy is. And then we can, and then we're done. We're able to define rough paths, right? Or rough integration. So the sewing lemma says that this has a unique solution if and only if A is what is called coherent or almost an increment, in the sense that the triple difference is small. Yeah. Yes. Yep. I think you can only, you have to carry this approximate thing around with you. But maybe for certain A, maybe you can make it exact, but.
Create a new structure, not a structure where it approximates this.
Yeah, by quotienting out or something, sure.
So-called theorems about boundaries and so on, turn it into a linear algebra problem.
I think this is the approach a lot of people take, though. I mean, they really view this algebraically like that, yeah. So let me say the sewing lemma is that so the sewing lemma says let A be a germ that is say gamma coherent, meaning that for all SUT, we have at least SUT in the 3 simplex. So just say we have there exists C greater than 0 such that delta A SUT then C T minus S, so 1 plus gamma. Okay, so if A is a germ that is gamma coherent in the sense that we're able to, we have this kind of Holder condition for something greater than 1, which should remind you of the Young theory, right? Then there exists a unique continuous linear I, so that I of T minus I of S minus A of ST. So let me say there exists another constant C prime. C prime is less than T minus S to the 1 plus gamma. C prime. So the sewing lemma tells us that given a that is approximately an increment, right? In the sense that the triple difference is approximately 0, then it's if the triple instrument is approximately 0, then I is approximately an increment. Okay. What was that? Oh, it's linear. So it's going to be linear. Just basically, I just mean it's linear in the time it's additive, right? You're going to have yeah. So it's the main thing I'm talking about here is just going to be the additivity of the T minus S, right? So really, some people write it as I of T comma S that is additive. I of T comma S plus I of S comma U is I of T comma U. Yeah. Yeah.
So it actually could be the way you define it.
Yeah. Yeah.
Something that
Mm-hmm.
So now you say it's not in the statement of exact.
Mm-hmm.
Say the internal would be
Mm-hmm.
going upward. Then you're in the image.
Mm-hmm. Yeah, that's right. No, I mean, that's exactly it. And if you think of this delta, it really is a boundary operator in the sense d squared is 0, right? Yeah. So,
This might be a big O of one. There you only need
right. Yeah, so it gives you a big O of 1 plus gamma, which for any purposes, the value of gamma isn't important. The point is gamma is positive. Yeah.
So it doesn't really matter what gamma is, it's for gamma, it's also true for half gamma.
It's not relevant from the point of defining the integrals that we want to define because it's going to go to 0 regardless. Yeah, so that's the point is in terms of defining the integrals, what the gamma there is, as long as it's positive, isn't.
One gamma fixed or one gamma at a time.
Mm-hmm. Yeah. So,
For smaller gammas, for bigger gammas. The bigger the gamma, the more fluid becomes. Right, no, but we didn't put in an output, right? So the question is, if you know for one gamma, can you compute it for you didn't put in output for another gamma?
I'm not sure about that actually.
When you call it a germ, that suggested that there's some, just depending on a neighborhood. I don't know if that's where that came from.
Yeah, that's absolutely where it comes from. Yeah.
Something from one plus gamma. Could we say any neighborhood, but I don't know if that's maybe we have to.
Yeah, I'll show you the proof. I mean, the gamma here is just as long as it's positive, we should be able to construct this I. Yeah. So so first of all, let me talk about the uniqueness of this. The uniqueness we get pretty much for free. And then the existence requires some work. So it's real uniqueness that if we have an I that satisfies or two I's that satisfy this, then they're literally the same I, right? And you can just check this out by, so proof. Let's start off with uniqueness first. So if I tilde satisfy, the conclusion, then just I minus I tilde of T minus I tilde of S. Then we can add and subtract the A of ST, right? Plus A of ST minus A of ST. Do triangle inequality, do, standard analysis, but just do triangle inequality with that difference, triangle inequality with that difference, apply the conclusion, and we get C T minus S to the 1 plus gamma. For triangle inequality, which because this is a natural increment, the I minus I tilde, you can just divide by T minus S, take the limit, get that the derivative of I minus I tilde is 0, right? So we can get uniqueness there. So uniqueness isn't too bad. And then
Variable version of that where you sort of, I mean, there you said, okay, you get a certain amount of order, then it's actually equal. two variable thing where you could say if some triple or double different thing, gain some derivative would have to be zero, and then something that you actually have a quality rather than just awesome.
Maybe, I'm not sure, but yeah, maybe. Yeah. I mean, people, the sewing lemma has been studied, a lot, and yeah, a lot of people are very interested in this and very interested in, generalizations of it. I've seen some papers with like the 1 plus gamma, like being relaxed to something less than 1 and seeing if you can get some kind of order out of this and a bunch of other things. So people have been very interested in generalizing the sewing lemma, and even, so the sewing lemma also is on the interval. So it's time, right? It's a one-dimensional input. If you have germs that depend on some spatial variable, the analogous result of this is what's called the reconstruction theorem from regularity structures. So there's been lots of generalizations, lots of thoughts. And this is kind of like, as you were talking about, like it does have a very algebraic flavor to it in terms of these boundary operators. Yeah. So we have the uniqueness. Now let's talk about the existence of such an I. And then so for the existence, first note that we can figure out what I would have to be before we know that I exist. We figure out what I would have to be, right? So for existence, what we do is first note that if we take a partition, P of ST, then we have I of T minus I of S minus, let's talk about, sorry, one second. So if we take a partition of S minus T, we can take this increment, and then we can talk about, sorry, let me write my notes. So give me 1 second. Actually, let me not do this. So basically, what we're going to do is we're going to take a partition. We're going to look at the Riemann sum here. We're going to look at this Riemann sum and then show that this converges, right? And if we can show that this converges, this is going to be our candidate I, and then we can just verify that I satisfies all of these properties, right? Okay. So now I remember what I was trying to say. So if we take this partition and then we subtract off, I of tk plus 1 minus I of tk, right? And we look at the absolute value of this, then this is bounded above by k equals 1 to n. And then I'm just saying, if such an I exists, we have this bound, right? Some C times tk plus 1 minus tk to the 1 plus gamma. And then this guy converges, right? This guy goes to 0, right? As the mesh size P goes to 0. So the point is, if I were to exist, it would have to be a Riemann type sum like this, right? So if an I exists, it is going to be this limit. Okay. So let's just check that this limit exists. Exactly. Yep, that's right. Just because of that property, we show that, it's going to have to be a Riemann sum. So let's go and show that this Riemann sum actually exists. And then once we show that it exists, then you have to check that it's additive and some other, just check that it's additive, which requires a little bit more work. But basically, we want to define I of t minus I of s. It's the limit as, say, a partition mesh size goes to 0. Okay. Right. So we want to define this. And if this limit exists, then we can do that. But all right, so I'm going to show using dyadics that we can just choose the partitions to be dyadics, and then we can show that this limit exists, and it's going to be exactly the same proof as the Young integral I showed before. Literally exactly the same proof. So we just take Pn to be dyadics. So that means it's just going to be k over 2 to the n, and I'm just restricting s comma t to be 0, 1, just in the interest of writing the partitions down a little bit easier. Okay. So in this case, we define In to be equal to the sum of k equals 0 to 2 to the n minus 1 of a of k over 2 to the n. Yeah, should be capital N, k plus 1 over 2 to the n. And then we can, again, just write this as I to the n is equal to I0 plus the sum from I n plus 1 minus I n from, k plus 1 minus I k equals 0 to n minus 1. Which is exactly what we did in the Young case. And then we just want to bound this guy again. And in order to bound that, we take a look at these two differences from n and n plus 1. And there's a very nice relationship that in plus 1 minus in is equal to k equals 0 to the 2 to the n minus 1 of the triple difference a of k over 2 to the n, and then uppercase n here, k plus 1 over 2 to the n, and then k plus 2 over 2 to the n. So you can just check this out for any a, which is where this triple difference is coming from. Is it's coming from the difference of these Riemann type sums. And then we can use the coherence or the assumption on this, and we can get that.
And that's, we're fixing it in and we're taking that's because of the partition size, right?
Yes.
And then we put a subscript on it. That means go a certain number of steps out. You just
Yeah. Sorry. There you go.
Okay.
Yeah. Sorry about that. You're
When you I superscript K, that means it's changing the partition.
uh-huh.
Certain number of steps in a given partition.
You're changing the partition.
Okay.
So we're just telescoping all of these partitions. So it's I0. So like I2 would be I0 plus, or let's say, yeah, like I1 would be I0 plus I1 minus I0, right? So, you know, you can keep on going. It's just a telescoping sum that we're getting for the IN. And as long as this thing is summable, then the limit of IN exists, right?
Each time we double the number of points in the previous sum.
Mm-hmm. Mm-hmm. Or at least double number of intervals, right?
Yeah.
Which might not be the number of points, yeah.
You do that in my note, but I guess okay, this is the ones that you could say this is just some where you add points at step 1, then you add points at step 2, but some points are already there.
Mm-hmm.
You just keep saying which you're this way, you're filtering along the level of steps at which you
Mhm.
enter. Okay.
Mm-hmm.
You have to keep this too.
Mm-hmm. Mm-hmm. Yep, that's right. Mm-hmm. Yes.
Yeah. Okay. Yeah. I just had to figure out what all that meant.
Yes. And then you're able to get this triple difference. Just make sure that you're able to get this triple difference here. Mm-hmm. Mm-hmm. That's right. And then, yeah, let me just make sure thing is good here. Yeah, so then you're able to get this triple difference here. And then it should be, then after this, you could just use the bound that you already had. And you get IN plus 1 minus IN is bounded above by K equals 0, 2 to the N minus 1, some constant times 2, let's say 1 over 2 to the N times 1 plus gamma. Just using the using what we had before. Yes, that was the coherence assumption. And then this is equal to just C over 2 to the N gamma, which if we replace that in there, is summable. Okay. So the point is you can take these differences, it's summable, and then you're able to gamma, sorry. All these letters, gamma. So then you're able to do that, then it's summable, and you're able to take that limit. And then in order to show, so this is an I of t minus I of s, to really show that it's this, that you're able to split it, requires a little bit more work. Or another argument is, rather than just using dyadics, is show that this limit exists for all sequences of partitions where the mesh size goes to 0. But you can show all of that, and you can show that it really does split like this. Okay. Right.
The areas you were referring to that you yes,
Mm-hmm. Yeah. So that's the thing, is the linearity we're requiring is just being able to. Yeah. And, you know, we show that there's an I of t minus I of s, or we show that there's an I of ts associated to this, and then showing the additivity, showing that it's actually an increment requires some more work that I don't have time for, but it does require some more work. Another way of proving it is if you show for any sequence of partitions that this kind of Riemann sum converges, then you can recover the additivity. Okay. But just showing it along these dyadics, you don't quite get the additivity, requires a little bit more. But I just wanted to show at least this part of it.
It's dyadic.
Yeah.
Dyadic points.
Yeah, you get dyadic additivity, which then requires you to kind of interpolate with dyadic points and things like that. Yeah. Yeah.
What I was thinking was, did you finish the proof?
I finished what I was going to present today. Was that? Yeah.
So we disproved that the I converge. Equals 0.
Mm-hmm. So the IN converges.
That's going to be our I.
We have to check that it is. Yeah, but you can build this. You can get that from here. Actually, you can get that from here, and then you can get the additivity. But the point is, this limit exists. Then you have to check a little bit more. But yeah, you do have to. Yeah. Uh-huh.
That was my question at the beginning. It said it just, but if you know it for one gamma,
Mhm.
tell you anything. Because the gamma and the hypothesis again
Mhm.
included.
Yeah.
Doesn't tell you anything for another gamma.
Not a priori. I think you can maybe say some other things. I'm not sure. But from the point of defining an integral, the value of gamma doesn't matter. From the point of defining the integral. Yep. Let me give you some examples of things that are gamma coherent. Okay. Because once we have the sewing lemma, then we can get, we just have to check the gamma coherence. So one example of something that's gamma coherent, example 1. So let F be in C alpha, G be in C beta, with alpha plus beta greater than 1. Okay. Define A of ST to be F of S, G of T minus G of S. Okay. So this is going to be the Riemann sum that you would get for just a standard Riemann Stolzsches. Then the coherence of A is going to be it's going to be F of U minus F of S, G of T minus G of U, which bounded above by Holder norm of F, Holder norm of G, T minus S to the alpha plus beta, which is greater than 1. All right. So the sewing lemma implies the existence of the Young integral. Right. And once you have the existence of the Young integral, let's talk about the rough integral as well. All right. So one other thing that is going to be gamma coherent, just I wrote it down, is going to be the, give me 1 second. Yeah, is going to be, example, if x2 is a rough path, you know, and let's say alpha is between 1/3 and 1/2. Define A of ST to be Y of S times X1 ST plus Y prime of S, X2 ST, where Y prime, where Y and Y prime is a controlled rough path, or is a controlled path by X, just meaning that Y of T is equal to Y of S plus Y prime of S, X1 ST plus a remainder term ST, where this is in C2 alpha. So it just means you have a Taylor type expansion. Then you can compute its coherence. UT. If you compute its coherence, it's going to be minus R ST X UT minus Y SU prime X UT, and then that is 2. There's 1, which again, it's bounded above by some constant T minus S to the 3 alpha. So this term here is coherent as well. So once you have this term that's coherent, then you're able to apply the Sewing lemma and get that the rough integral exists. Okay. And then let's say you had a higher ordered one, X, X2, X3, where alpha was between 1/4 and 1/3. You had a Y, Y prime, Y double prime. You could take the coherence and you get something that is in 4 alpha and 5 alpha, and you can show this. Some of the algebra gets kind of messy, but the point is you're able to define the rough integral as the limit of this AST. So this shows that the rough integral actually exists. If you just take this coherence here. So this inequality here, so that is 2 alpha, that is 1 alpha holder, that is 1 alpha holder, that is 2 alpha holder. You apply triangle inequality and then you apply the alpha holder on each one. All right, so we can, so we've been able to show the existence of this rough integral. And let me just, a few more minutes, let me just give kind of a broad picture of, you know, rough paths of, you know, the entire story that we've covered. So, and mention some things if I had more time that I would like to talk about, but let's say you have, you know, the differential equation, dy is equal to b of y, dt, plus sigma of y dx, right, where x is in c to the alpha, alpha is between 1/3 and 1/2. Then there exists by Lyons-Victor or other approaches, Lyons-Victor. An X2, you know, an X2 process satisfying Chen's relation, satisfying that it's 2 alpha holder, so that, you know, X1, X2 is a rough path. Then once you have this, then you define the, let y be controlled by x. Which is just meaning something like y is equal to f of x, or y is, we're going to soon say, or, soon you can hear that it's going to be solution to RDE. Okay. Then this limit here, y of tk, x1 tk, tk plus 1, plus y prime of tk, x2 tk, tk plus 1 exists. And this is called the rough integral. I said y equals f of x as an example, or y is a solution to an RDE. So it's just as examples, controlled by meant you have this Taylor type expansion. Then this limit here exists. We call it the rough integral. And we denote by where here we can say bold x is equal to this rough path. We call it this rough integral, and solutions to, also it's not something we've talked about, but solutions to one exist if vector fields are, there's many conditions, but if the vector fields are, say, I know one of the first ones would be C3, but you can reduce to Lipschitz and everything. Solutions to one exist, and this is done by Picard iteration. Okay. And then now we have a theory of differential equations of stochastic calculus for any path that is between 1/3 and 1/2, and then we can keep going down to lower orders as well. And then from this, there's a lot of other things we can talk about. So we can talk about things like Freeland-Wenzel large deviations, Struck-Varadhan, support theorems. We can talk about, extending this to stochastic PDEs, for example, all sorts of other things that, we haven't gone to. Or tomorrow I'm going to be talking about how we can apply this to stochastic control. Mm-hmm. Well, it's just going to be on the solution. So it's just going to be yeah.
That's in board.
Mm-hmm.
The summation says y of tk. That's 1. Tk plus 1.
TK plus 1. Yep.
Oh yeah. 1.
Right. X1 is that's just the increment of X1. Yep. So then we call this the rough integral, and we have solutions to one exist, then we're able to do all of this other stuff with it that if I had more time, we would talk about. And let me conclude with just one small little fact about rough paths now that we have all of this. One small last thing, and then we can conclude, but so. Yeah, we choose the left point TK. It does not depend on the sequence of partitions, but we do choose the left TK. And if you change the TK, it's going to change.
Okay, look, it's also dependent on that.
Yeah, it's going to be this left endpoint. It's just going to be like a standard Riemann Stolches with this additional correction term. It'll be something different. I'm not sure. It'll be different though.
I thought that at this point, the part is the rough part. Not on the choice.
In here, I think it'll depend. Maybe you can prove that it doesn't, but at least a priori, it does depend. And I think that's just true in general. Oh. Mm-hmm.
And then plug it back to the SDB, and then
Yep. Yeah. So basically, you take a guess, you plug it in here. You're able to define this as a rough integral. This is just a Riemann integral, right? Then you get update a y2. Then you get another update a y3. You just keep plugging it back into this equation, and then you get a contraction principle to the solution. So there's multiple things you can talk about. The one one really first one would be like if they're C3, if they have 3 derivatives. That's one you can do. People have dealt with like less and less regularity, and people have gotten into, you know, how bad of regularity can you be, a million papers and things like that. But one first case is going to be if the vector fields are C3. And then you can weaken it to Lipschitz, weaken it to some other things as well. I know some work that's been done on weakening it to where the vector fields are even holder, right? So as long as the vector fields holder and the rough path holder kind of sum up to greater than 1 in some ways, you know, you can do some things like that. Yeah, so well, so I'm saying if we're given an x and x is C alpha between 1/3 and 1/2, then we only need up to 2 iterated integrals, right? Well, y is going to be, it's a controlled rough path, so it's not going to necessarily have iterated integrals. So you don't need to talk about the iterated integrals of y here. Yes. That's right.
We're going to say something y instead of x, capital F is something.
Yeah.
We do get to bank in the past.
Mm-hmm. That's right. So you plug in, say, some smooth y here, then you have a sigma of y, and then you plug in another one, and then you plug in another one, and you plug in another one, and then you can show, I mean, it's not an easy proof that it works. It's pages and pages, but you can show using this Picard iteration.
Or alpha order. Second derivatives kind of version of that whole thing.
Well, the sewing lemma works for anything at all. It's just a generic A of ST.
Now,
Oh, if you're interested in more variables. Yeah, you can do things like that. And you can also do things where, so the main thing that people care about is going to be generalizing it from S and T being time points to S and T being points in space. So rather than being a rough path, it's going to be, you know, it's going to be like a field. That's the thing people have generalized the most. So that's going to be for like stochastic PDE, where the noise is going to be a field rather than just a one-dimensional path, right?
Put in part of a boundary.
Mm-hmm.
Together, right? So we capture the chunks.
Yeah, and all of that is regularity structures, generalizing this from one-dimensional time. If I can give one short, small proof, I know I'm probably like over time a lot, but one thing that it'll be very short and I think interesting, and Serdar is would be hopefully very interested in. let me just. So let's say you take a trapezoid rule. So let y of tk plus 1 plus y of tk plus y prime of tk plus 1 tk plus 1 plus r tk plus 1. And y is just a one-dimensional, and then x is in C alpha between 1/3 and 1/2. Then if you just take then you plug in this guy right here to here, and this is over a partition P. Some partition. This is equal to y of tk, x1 tk plus 1 plus y prime tk, x1 tk plus 1 squared by 2 plus 1/2 r tk plus 1 times x1 tk plus 1. First guy here is the rough integral. If we just talk about the geometric path as x squared by 2, this part here is of order 3 alpha. So that part goes to 0. This part goes to the rough integral. So this whole thing goes to y of s dx of s, where x is enhanced with the canonical geometric rough path. Just yep. So here I'm just considering a one-dimensional path and alpha between 1/3 and 1/2. If you want to go down to higher dimensions and lower regularity, you have to use the Gaussianity, the properties of that, and covariances and stuff like that. But this works for any x in C alpha between 1/3 and 1/2. You can just take the trapezoid rule and it converges. Or Stratonovich.